Welcome. This is day 2 of section 7.1, Introduction to Graph Theory, and today we focus on Euler trails and circuits. An Eulerian trail, or circuit, is a trail, or circuit, that uses every edge exactly once. So every edge exactly once. A graph with an Eulerian circuit is called Eulerian. We say this is an Eulerian graph. Now, this graph that you see here, the envelope graph, this graph has an Eulerian trail. So do you remember that? We can find one here. Let's start at 3. And I'll start there. I'll go to 4, 6, 5, 2, 6, 3, 2, 1, 5, and then back down to 4. So I covered every edge exactly once, but since I started and ended at different places, it's not an Eulerian circuit, but it is an Eulerian trail. But we're guaranteed that this does not have an Eulerian circuit. I'm promising you it doesn't. Why not? What is it that prevents this from having an Eulerian circuit? And I want you to think about that. You can even pause and think about it for a little bit. Why does this not have an Eulerian circuit? All right, I'll tell you the answer. Let's think about this vertex at 3. Notice that it has degree 3. So suppose that I'm trying to make a circuit, and I start at 2, and it shouldn't really matter where I start, because if it's a circuit, you'll start and end at the same place. I start at 2, and I make my way down to vertex 3. At this point, I have two choices for leaving vertex 3. It doesn't matter, just pick one, and we leave this. And now we're continuing on, and we go on our way, and we continue trying to make a circuit. But what has just happened here? Since it only had degree 3, I've already used up 2 of those edges. So the next time I visit vertex 3, and you know I have to visit vertex 3 again because there's this edge here that hasn't been used. Eventually I have to use that edge, so I'll be coming in to vertex 3, and then I'm trapped. So what was it about vertex 3 that caused problems? That same problem doesn't exist at, say, vertex 2. If I start at 3 and I visit 2, I can leave 2 and continue graphing, and then at some point I'll come in to 2 and I'll leave 2, and that's okay, I can continue, and eventually maybe make my way back to 3. I think you see it right. The problem is that vertex 3 has odd degree. Because it has odd degree, I can't enter and leave, enter and leave, enter and leave, indefinitely. I can enter and leave the vertex a certain number of times, but then eventually I'm going to enter the vertex and not be able to leave. So it's this vertex of odd degree that messes things up. Well, here's Euler's theorem. If every vertex of a connected graph has even degree, then the graph has an Eulerian circuit. Corollary, if there are exactly 2 vertices of odd degree in a connected graph, then the graph has an Eulerian trail. So in fact, I'll go back a slide. That's exactly what happened here. Here's a vertex with odd degree. There's a vertex with odd degree. Those are the only 2 vertices with odd degree. So in fact, any way that you try to make an Eulerian circuit, well, you can't do it. But any way that you try to make an Eulerian trail, it must start and end at vertices 3 and 4. Does the graph have an Eulerian trail? Is the graph Eulerian? Go ahead and pause the video, take a look at these things, and come to your decisions, and then start again when you're ready to check your work. All right, let's take a look. On the left, every vertex has even degree, so this definitely has an Eulerian circuit. And then it's fun just to try to make one. How about if we start at 11, see if we can trace everything and end back at 11. All right, moving on to the middle graph. Let's see, where are the vertices of odd degree? Okay, lots of vertices with odd degree. Does this have an Eulerian circuit? Definitely no. Does this have an Eulerian trail? Definitely no. I can only have, if it only had 2, then I might be able to make a trail, but not with 8 vertices with odd degree. Moving on to graph 3. Let's identify the vertices with odd degree. I think it's vertex 2 and vertex 9. So there is an Eulerian trail, but there's not an Eulerian circuit. Let's see if we can find the trail. I'll start at 9 and I'll try to end at 2. There we go. That's kind of fun. You should try it on your own too. There are lots and lots of solutions. So what is the answer to the Königsberg bridge problem? Now we can answer it. Now we can tell those people from the 18th century the solution. And I look at this graph, let's see, odd degree vertex, odd degree vertex, odd degree, odd degree. Man, they are totally out of luck. Every vertex has odd degree, so there's absolutely no way that this graph is Eulerian. You can't start at one spot, cross over every bridge, and come back to your starting spot again. In fact, since it has more than 2 vertices of odd degree, it doesn't even have an Eulerian trail. You can't even start at one spot, travel over every bridge, and end someplace else. Now, if only maybe there was an extra bridge that connected B to D, right? And then I'll make a little bridge there in the picture. If that was the case, then the only 2 vertices with odd degree would be A and C, and we could find an Eulerian trail. There are some interesting problems where we don't have a graph, but we have sort of a quote, real-life situation, and we need to make a graph. So how about this one? Is it possible to tour the following museum, passing through every doorway exactly once? A good thing to begin wondering is, what's the graph? Do you see it? All right, here it is. I'll show you. We want the graph to be so that edges go through doorways. The question asks, how do I do this so I can pass through every doorway exactly once? And this is like traveling on a graph where every edge of the graph is used once. So let me get rid of the original building picture. There we go. And now we're just left with a graph. Can we do this? Can I start at the entrance and end at the exit and hit every edge exactly once? No, the answer is definitely not, because we have several vertices of odd degree. If it had only been the entrance and the exit, then that would have been fine, but these other ones make the task impossible. Here's another one. So definitely you should pause and try at this point. What is the graph that represents the underlying movement in this picture? Is it possible to tour this following museum, passing through every doorway exactly once? How do you make a graph where the edges represent doorways? And I guess the vertices will represent rooms, so see what you can do. All right, go ahead and give it a try right now. All right, so here we go. Here's how we might start. So I need a graph where the edges go through the doorways. And this is a good start. The thing that's really messing us up is this hallway that goes around everything. The hallway is a room, and when I'm in the hallway, I actually have 8 different doors that I can go through. The entrance, the exit, the 2 on the top, the 2 on the bottom, and 1 on each side. So when I make this graph, here we go, I'm left with something like this, but like this point, and this point, and this point, all these points actually represent points in the hallway, and they all need to come together. So I might actually amend my graph a little bit like this. There we go. It's a little bit weird, right? But I'm sort of making sure everything meets right in the top center. We'll call that the hallway vertex. So at this point, can we answer the question, is it possible to go through every doorway exactly once? And I think it is. This one vertex has degree 8, but every other vertex has degree 4 or degree 2. So it is possible to solve this problem, and I will leave that to you. Can Sara and Emily cover the following city map, visiting every street exactly once? So there are a couple problems here. Let's first imagine that maybe they travel together. They work together. Can they cover every street exactly once? Also, can they do it starting and ending at the same spot? Or maybe they don't care about that. They just want to start someplace and they can end someplace else. That's fine. Pause the video, think about this for a little bit, and see what kind of solution you can come up with. All right, and then when you're ready, Here we go. Let's start talking through the solution. The first thing to do is identify the vertices with odd degree. So 1, 4, 5, and 10. So definitely there's not an Eulerian circuit. This is not an Eulerian graph. And there's no Eulerian trail. So they can't start and stop at the same spot, and they can't even, if they're traveling together, they can't cover the whole city. But what about if they split up? So let's suppose that they do. And Sarah says, tell you what, I'm going to start at 1, and I'll go from 1 down here. And let's say that she's going to travel a little bit and make her way to vertex 5. There we go. So she started at a vertex with odd degree. She ended at a vertex with odd degree. Look what's happened. Now, the vertices that were interior to her path, like 7 was originally even degree, and Sarah, I'll identify Sarah. Sarah used up 2 edges. Oh, so it still has odd degree for the edges that remain. Same thing with 8, same thing with 9. And 5, it used to have odd degree, but now it has even. I mean, subtracting out the edge that Sarah used. And same thing with 1. It used to have odd degree, but now that Sarah has used one of the edges, then an even number of edges remain. Now, Emily needs to start at a vertex with odd degree, so her choices are either 4 or 10, and she ought to be able to make it from 4 to 10, hitting all the remaining edges. Let's give it a try. Let's say she starts at 10. Aha, and look at that. She was successful. So between the 2 people, we have 2 Eulerian trails that can cover the whole graph. So let's talk about adding the fewest number of edges possible to make a graph Eulerian. Because if it's not Eulerian, then it has some vertices with odd degree. This first graph has 6 vertices with odd degree. And so if I pair them up, I'll say maybe I'll draw a new line from 2 to 8, and it's okay. So now I have multiple edges between 2 and 8, but that's fine. Or an edge from 3 to 7, an edge from 4 to 6. Now this new graph with my added edges, that is Eulerian, because now every vertex has even degree. How about the graph on the right? What do you think? So lots of vertices with odd degree, but if I pair them up and draw new edges between them, then the resulting graph is Eulerian, and it took us, well, in this second case, it took us 4 edges. We needed 4 new edges because we had 8 vertices of odd degree. And so it should kind of make sense. However many vertices of odd degree I have, divide that by 2, and that's the number of new edges you need to add. So give it a try here. What is the fewest number of edges possible to make each of these graphs Eulerian? All right, so here we go. In the first case, it is 5. I could maybe add them like this. And in the second case, I only need 1 new edge from 9 to 2. There we go, and now every vertex has even degree. What's the fewest number of times you must lift your pencil to draw each of the following without retracing your lines? So at first this seems like an Eulerian trail problem. Let's take a look at graph A. The vertices with odd degree are there. And so if I were to add an edge there and an edge there, this graph would have an Eulerian trail. And so those 2 dashed lines, they could represent points where I sort of lift my pencil. So let's go ahead and give this a try. But whenever I need to use one of the dashed lines, we'll call that lifting my pencil. Okay, so here we go. I'll start at the bottom arrow. All right, so I'm stuck on the original graph. So I need to lift my pencil. So I follow the dots. And I can continue on, go here. Up, I'm stuck again in the original graph. I lift my pencil, go over the dots, up, and there we go. And I ended up at the second arrow. So I had to lift my pencil twice. So with three pairs of vertices with odd degree, I actually had to lift my pencil twice. Okay, and I will let you figure out the solution for graphs B and C. And at this point, I'll stop. This is kind of an interesting idea, right? These are puzzles. These are fun games. It's just kind of neat to look at these graphs and think about Eulerian trails, Eulerian circuits, and can I trace it without lifting my pencil? All right, I'll stop here.